All right, the introduction to cross sections. We're going to hit a number of different topics fairly quickly, and then try to move on to volume. These are all standards that need to be presented, but will not be focused on greatly in tests or quizzes. There will be test questions on these, though. So, cross sections and solids of revolutions focus on prisms and cylinders. So they start out and they say sketch a rectangular prism and a cylinder. I think that's always a good idea, you guys. I would, when I sketch these, I start out with a rectangular prism. I start out simply just drawing a rectangle that I'm working with. Okay, and it probably should try to be neat, but that's the front face. I then, up to the right and off to the side, I draw the back edges. Now, those are only the things that can see. Now, I'm going to complete that rectangle with dotted lines because theoretically you can't see those, right? This edge you can see, this edge you can see, this edge you can see, this one you can't. And you have a rectangular prism. And you can do that with any uh, prism shapes. The cylinder can be done in a couple of different ways. It's probably easiest to start with the top circle drawn as an oval, and then depending on how big you want it, the bottom circle uh, with the top part of it dotted, and you end up with a cylinder. Somewhere, whether it's on the top or the bottom, you're going to draw the radius, whatever the radius is, and work from there. Um, you can always, do the same thing this way, depending on how you want that perspective. And that's true. Um, and having those side by side make it a little bit more difficult um, to see, to visualize. Okay, we're going to jump to page 83 on this. The boxes are obviously important here. Another way of saying the same thing is to say that the lateral edge of a general cylinder are perpendicular to the bases if the figure is a right figure. If the lateral edges are not perpendicular to the base, then the figure is oblique. Now, we probably could have drawn more of an oblique prism if you really wanted to. Um, a cylinder that is more oblique might do something like this, where this is drawn not at a right angle. This down here would have been a right angle. These here theoretically would have been right angles, is what that says. So we're going to deal with both right prisms and oblique prisms. So this oblique is a term that just means it's not going to be a right angle. Cross sections and um, slices, there's a difference. A cross section basically just says that um, the sliced through the middle is going to be parallel to the base, whereas a slice is definitely not parallel to the base, and in some cases creates a different shape. Okay, and that's a difference that we need to pay attention to. Um, they asked us to sketch the cross section for the following figures. Um, and so I would just take a minute and go through that. This way, a cross section would be a round section here, and it goes back like that. That's just going to be a circle, right? Same thing's going to be true for all of these, right? That's just going to be a pentagon. So the last two I did, so the video doesn't get so long. You get the idea, I hope. Okay, this is an interesting concept that ultimately will lead to calculus. So this is why they're introducing this. So you have to imagine here a toothpick with a post-it put on the toothpick. And as you spin this around, visually, you will end up with a solid, and it looks a little bit like a cylinder, okay, when you spin that around. That's the case here, where if this gets spun around, right, you're going to end up with something that looks like this. That gives you this cylinder shape. And again, this can be done with all kinds of different shapes. It's kind of interesting to play with this. Uh, a solid of revolution is a three-dimensional figure obtained by rotating a plane figure or curve about a line. So they ask us to do this a couple more times. Uh, this ends up being a sphere. This one ends up being a cone. This one will end up being they call this a frustum. Okay, and as you rotate those, the sphere, you're going to draw, so it looks something like this, and it has a radius, right, that in the middle. Um, this ends up being a cone. That's the height of the cone, if you will. And then this one ends up being somewhat interesting, where you have uh, two different sizes of circles. And basically what this is a cone with the top lopped off. Um, anyway, kind of an interesting scenario. Moving on to lesson 9, by the way, we are on page 89. Introduces pyramids, cones, and again, their cross sections and then the relationships between those. Um, with the cross sections of prisms and cylinders, the cross sections were identical. In this case, you'll notice that the cross sections here tend to be smaller than the base. And what we're going to discover, or we're going to figure out real quick, is that these end up being proportional um, to each other in the same way that the sides are proportional. Now, I'm going to let you guys, if you want, go through this yourself, but I'm going to move on a little bit so that we can keep this video shorter. Notice that the ratio of the sides is 3 to 5. That's your ratio. Okay, that's important. When you get to questions like G down here, they're saying that uh, the area is also proportional, and we've done this before, right? We know that if the ratio is 3 to 5, the ratio of the sides, then the ratio of the areas is 9 to 25. If the area of the base is 25, then you're looking for the cross section, and clearly C has to be 9 millimeters squared. Now you can cross multiply and solve that, but that was the idea. So we're going to continue with that, and we're going to look at problem number 2 here, and you guys can read the blurb above if you need to. I won't read it to you on the video. They're giving us a triangular prism, and they're giving us some information. The distance from X to V is 18. That's the height of the whole pyramid. Distance from X prime to V is 12. That's the height of the smaller pyramid. And the area of the cross section is 28. What is the area of ABC? So we know that the ratio is 12 to 18, which can be reduced clearly to 2 over 3. The ratio of the areas then is going to be 4 to 9. And we know that the area of the cross section was 28. So the cross section, or I should call that the base, I guess, shouldn't I? The base then is what we're looking for. 4b equals 9 times 28. You guys, you'll notice that I often don't multiply those out, and there's a reason for that. Big numbers get scary. When I simplify things here, it's easier to see that 4 goes into 28 7 times, right? These leave ones here. And my base now is equal to 9 times 7, which is 63 units squared. So you can do that with a calculator. I don't do a lot of this with a calculator. It's just some number sense. All right, 2 more quick problems to walk through. The area of the base of a cone is 16. The height is 10. Find the area of the cross section that is a distance of 5 from the vertex. So you guys, I think it's helpful to be able to draw these things. So I'm going to go ahead and draw the cone. No, it isn't pretty. Where the height from here to here, right? That's your perpendicular base, is 10. And the area of the base is 16. Just call that B equals 16. And then they've got this cross section somewhere here like so. And that height there is 5. So let's go ahead and set up our proportion. We know then that we have a ratio that is 5 to 10, which reduces to 1 over 2. The ratios of the areas, oh, come on. Ratios of the areas is equal to 1 over 4. And if I set that equal to my area ratios, I'm looking for the cross section over the base, which is 16. Cross multiply and solve. I'm going to come up here. We get 16 is equal to 4c. Divide by 4. Right? And we end up with c is equal to 4 units squared, whatever those units are. Last one, number 6. They are trying to get you to look at similar bases and similar cross sections. The answer to this, if you read through this, is simply 30 units squared. They're going to be the same. The cross section areas of the cross sections are equal if the areas of the bases are equal and their heights are the same.